could be wrong about that. Is that plus 8 or minus 8? Let me rewrite this. This is minus 8 times lambda minus 4, right? Okay, I believe. Okay. And then what? What'd I do? Okay. So minus lambda squared plus 6 lambda minus 8, which, let me be civilized and factor that minus out, plus, minus, plus, there. Now I'm in my happy place. Oh, so this is also lambda minus 4 times lambda minus 2. So what we get is minus parentheses lambda minus 4 quantity squared times lambda minus 2. And then how do you find eigenvectors? What are the eigenvalues here this time? So we have lambda 1 equals to 4, right? And it has, what's the algebraic multiplicity here? I heard a 2, yeah. So we need to find basis for A minus 4I, right? Oh, I'm sorry, the null space. The null space of A minus 4I is equal to the eigenspace of, lambda equals to 4. And then for lambda 2, which is apparently 2, right, I have to find basis for the null space of A minus 2I. Now, you guys know how to do that systematically. You do the row reduction. You express the pivot variables as dependent on the non-pivot variables. And then you can use the non-pivot variables as parameters in the solution, right? As many parameters is as many, you have as many parameters as you have linearly independent solutions to the null space problem. But it's an equally important skill to be able to just eyeball it. Like this over here. You should be able to look at this matrix and go, you know what? 1, 1. That's the vector that I multiply this to get 0, right? This one here, quite clearly 1 minus 3 is the thing I multiply this to get 0, right? Because if I took 1 minus 3, then it just dot products with this and that to give 0. So yeah, I mean, you can fall back on calculation, but you also maybe you should at least have a shot at just seeing it. I'm not sure whether we can see these just from looking. What's A minus 4I? Probably not, actually. Minus 4, 0, minus 4, 2, 0, 2. Oh, look at that. 2, 0, 2. This is A minus 4I, right? And what's my A minus 2I equal to? So, all right. Do I need to do a bunch of row reduction? No, not really. This right here tells me that U plus W equals to 0, and V is free. So my vector 1 will have, my UVW vector, in other words, a vector which is a eigenvector with eigenvalue 4, I can tell you what it looks like. It's, minus W, comma V, comma W. So that's W times minus 1, 0, 1, plus V times 0, 1, 0. So minus 1, 0, 1, and 0, 1, 0, those are a basis for the lambda equals 4 eigenspace here. How about the other one? In contrast, the A minus 2I has 2 independent rows, right? You can look at it, just look at it. The first and third rows are the same stupid equation with the minus. The middle one is different. And so, I don't know, maybe I do the row reduction on that to see what to do. But after we do, we should just have, we'll have 2 equations. We'll have one non-pivot column, and so one solution. Something you should be noticing and not surprised by is every time we find an eigenvector, we don't just find one, right? Think about this. If I have AV equals to lambda V, take this equation, multiply by k. Multiplying by k gives me A times kV equals lambda times kV, because we can move the scalar multiple inside, right? What's that say about eigenvectors? You shouldn't be surprised when you find that there are infinitely many choices. There will be infinitely many choices if we're working over a characteristic zero field, because any scalar multiple of an eigenvector is still an eigenvector with the same eigenvalue. See, this equation and this equation both say that this says that V is an eigenvector with eigenvalue lambda. This says that KV is an eigenvector with eigenvalue lambda for the matrix A. So this thing we're finding, all of our answers so far, we haven't found just one eigenvector, right? We find a scalar multiple, there's a whole family of them. We just pick one of them to find a basis, that's all. That's just a choice of basis, right? But you also see that that's ad hoc, right? Like, why did I write down, I've erased it, but why did I put, the one I did there? Why did I put 1, 1? Why not 2, 2? Just a choice to make it pretty. I mean, I like integers, not fractions. That's pretty much it. But that doesn't explain the 2, 2 versus the 1, 1, does it? So, all right. I'm going to stop talking about 2, 2s and let you guys go. So. You guys seem tired.